Hi, guys. So, you get the honor of my first ever video lecture. I'm hoping this will work out pretty well because you can stop, you can pause it whenever you want. If you're having trouble getting the notes down fast enough, pause it, take a break. If you need to go do something else, stop, no big deal. We won't have to deal with all the regular classroom interruptions, and I can kind of check and see how you're doing. So, what is science? Science. The whole point of science is to figure out how things work in the world, things in the natural world. So we're not talking about witchcraft or magic or anything like that. We want to figure out an explanation for how something works in the natural world. Um, what science is and is not. Biology and science as a whole. It's not just a bunch of facts that are never going to change. We're always learning new things, we're always learning different things. It's never going to stay the same. Some of those things will change this week. Some of those things will change this year. Some of those things, it might be 100 years before we figure out it's not quite right. We might be totally wrong. It might be just a minor revision. All right, so the definition of science: an organized way of gathering and analyzing evidence about the natural world. So we can use science to learn about animal communication, like whales, how they're traveling in the ocean, where they're traveling to, and how they are affected by things changing in their environment, the water temperature, the water pollution, other animals that live in the water, whatever. Again, only dealing with the natural world. No magic in this class, sorry. Scientists collect and gather information in an orderly way, and that allows us to look for patterns and see how things connect to each other. Scientists propose explanations based on evidence, not just, well, I think this. In science, you have to have some sort of information to back that up, not just, I think grass is green because I like green. No, there has to be a reason for it. Um, we're going to skip that slide. This is important. Science doesn't usually prove anything. There are very few things in science that we know 100%. A lot of it's just like, yes, we have a lot of evidence to support this idea. We're pretty sure this is right. But in 100 years, that could change. All right, the scientific method. I know you guys have used this before in junior high. You're going to use it again in biology and probably a lot of other classes in your high school career. And if you go into just about any field in college, you're going to use the scientific method to some degree. So, observing and asking questions, making inferences and forming hypotheses, conducting controlled experiments, collecting and analyzing data, and drawing conclusions. We're going to talk about each of those steps on the next several slides. So, observing and asking questions. So, observation, just seeing something, describing it. So, maybe you see this area with grass growing, and in one spot the grass is growing taller than the other. So, that's going to lead us to think, well, why is the grass taller over here than over there? So, from there, we're going to make an inference, a logical interpretation. And then that's going to lead us to a hypothesis. I know you guys have learned about a hypothesis before. They call it a scientific explanation that you can test and find out if your hypothesis is right or not. Usually in elementary school, the definition they give you is an educated guess. That's still right. This just kind of explains it a little better. So the example of this grass here, their hypothesis was that it was limited by the amount of nitrogen available to it. So once you come up with a hypothesis, you have to design an experiment. It has to be a controlled experiment. It have to make sure everything about the experiment is controlled except for whatever variable you're testing. Hence the name controlled experiment. So whatever variable you are changing is called the independent variable, also called the manipulated variable, because you are manipulating whatever that variable is. So in this case, it would be the amount of nitrogen. And whatever changes as a result of your manipulated variable is called the responding or dependent variable, because it depends on how you change the independent variable. Okay, so usually an experiment has a control group and an experimental group. So they're both going to be the same except for one variable. The experimental group is going to be the one that you change that variable. So in this experiment they show you here, it's also in the book if you want to look at it, but they picked out 2 plots of marsh grass. All the other variables were the same, and one plot they added nitrogen fertilizer. So that's the independent variable. That's the variable that they are manipulating in their experiment. And then from there, they're going to look at how the marsh grass grows. So the growth of the marsh grass would be the dependent variable, because it depends on how much nitrogen they put on it. Okay, collecting and analyzing data. So we've got 2 types of data, quantitative and qualitative. So if you think about those 2 words, quantitative sounds an awful lot like quantity. So quantitative is something you can measure or count. Qualitative sounds a lot like quality. So it's something you can look at the qualities of, like color. So again, quantitative, something you can countermeasure. It could be the number of plants, the size of the plants, how fast the plants are growing. Qualitative, they give some good examples here. Foreign objects in the plots. If the grass was growing off to the side instead of straight up and down. The color of the grass, those would be qualitative. Research tools, in some cases it can be something really simple, a ruler, a meter stick, or it could be some fancy piece of electronic equipment that's going to measure how much nitrogen is in the soil or in the actual grass. And then we can use charts and graphs to organize the data. So here they're just graphing how high the grass grew. They've got time measured in weeks and the height of the grass measured in meters. And as you can see, the control group didn't grow near as fast as the group where the nitrogen was added. Okay, in the past, we wrote this all down in notebooks. It took a really long time. Now we use everything in computers. It's really fast, a lot easier. We don't have to spend time making a graph or putting our data points in order or whatever. It saves a lot of time. It's a lot more efficient. The computer is a lot less likely to make a mistake when making a graph than we are doing it by hand. Sources of error. Obviously, tools aren't perfect. Maybe your ruler wasn't made quite right. It doesn't measure the grass exactly. Even electronics, not always going to be 100% accurate. A lot of things you have to calibrate to make sure it's measuring correctly. Let's see. So after we get our data, we have to look at it, see if it supports our hypothesis, if it refutes it, if it says, hey, this hypothesis was totally wrong, or if we just need to change our hypothesis a little bit to come up with our conclusion. So again, the grass grew taller when we added nitrogen, and we're almost out of time here. Okay, so ignoring all this text off to the side, this flowchart shows it really nicely. You make your observation, come up with a hypothesis. Okay, sorry, I got interrupted there. So come up with your hypothesis, design your experiment, collect your data.